all those pieces of information is what I think is my job. Figuring out how to use that information and making something cool with it. So my background, so I'm a data scientist at OmniEarth, same place that Chelsea is, but I'm not a data scientist by training. As a matter of fact, I think data science is kind of a new job description, and I've met so many different types of data scientists. So I've met psychologists that are data scientists and statisticians that are data scientists, people with BAs and PhDs, so it kind of runs the gamut, and it really depends on the application. My background is in astrophysics. I have an astrophysics degree from UT Austin, a PhD, and undergrad I did physics at a liberal arts school in South Carolina, and I also studied art, so kind of a random meandering way to get to data science. But nonetheless, I think it's a very applicable position. So what is it that I do? In the context of geospatial analysis, it's all about analyzing and aggregating different types of data using a variety of tools to understand a larger problem. And really those different types of data, in this case, are typically imagery or raster data, which has band spectral information. So not only do you get kind of the geospatial context of where things are located on the globe, you also get information about their underlying physical properties that make them kind of shine or reflect or emit at different wavelengths of light. So you get that kind of multi-dimensional look at what an image, what an object in an image is. And then, so there's that raster component, but then I also combine that information with a lot of vector data. So I don't know how familiar you are all with those concepts, but you know, vector data is more kind of tabulated spatial information. So you can overlay it on top of raster data, and usually there's attributes, but basically it's all about the magic of combining those things. And then there's other pieces of that. So, you know, those are the main data sources, but then what kind of algorithms and tool sets can be layered on top to answer a specific question. So really, in the context of what I do, a geospatial data scientist is kind of a person that is adaptive at bringing various tool sets from a variety of backgrounds and can use them quantitatively and qualitatively to provide insight to a customer question or an interest. And then really, the way that all gets stuck together is with code. So it's a lot of computer coding. And there's this kind of corny, I think slightly, I don't know, weird term that people use in this world of data scientists called unicorns, where it's basically just you're defining this person that can do all of these things and do it quickly and efficiently. So hopefully that helps. But kind of one of the first things that I did at OmniEarth was, before I knew anything what was going on, I didn't really understand what a data scientist was. I didn't know precisely what I was doing, but one of the first things I did was come up with this graphic of what it is OmniEarth's main product is. And so it sounds like Chelsea has already talked a little bit about some of the water management things that we do. But basically, I like this graphic because it's data science in a nutshell, but it's also really driven to one of our current focuses in OmniEarth. And that is, you know, the question is specifically for California, but could be applicable for many other regions. But where does residential water use go? And in particular, where does external outdoor water use go? And so that's kind of the underlying question. But really, to get to that point, it's all about this data assimilation. So we have a land cover classification that is derived from our imagery set. So whether that's satellite or that's aerial data, you know, we have to define that layer. And then on top of that, we layer with parcel information. So now we have, you know, a beautiful image of, you know, what types of trees are in a particular parcel, and if there's a pool and if there's grass. But then on top of that, we want to be able to know, okay, how do we correlate those trees and pools and buildings to an actual address, so that parcel or vector information gets sandwiched on top of that. And then, you know, in the chance that we get water data from somebody, you know, a provider, we can tie that individual parcel level information to the actual water use that the person uses. But underlying to that, to actually predict how much water this person at the parcel level needs, we use that land cover information combined with this water budget by parcel, a scientific expression that takes into account climate and variability, seasonality and the region of where the person lives. And it can give us an assessment purely based on the imagery, how much water they should be using relative to what other people are using, and given the types of whether it's a pool or it's a tree or grass, how that water is distributed. And so this is, when I first put this together, I had really no clue what it was, what the product looked like, and I think we were all trying to figure it out still. But I think now, standing back a year later at OmniEarth, I have this clear picture of all the pieces that go into this problem, and really, I think it captures a lot of what data science is. So are there any questions so far?
I have a question, Shay.
Yeah.
I'm just wondering, can you talk a little more about what goes into calculating a water budget? So you talked about, we use the land cover class, but then there's all these other factors that you guys are considering, whether it's, weather, ET, slope, all these different things. Can you just talk about that component a little bit?
Yeah, absolutely. And I have a couple of other pictures of this that we can talk to as well. But,
perfect. Okay.
But yeah, so kind of on my end, I'm really down in that pixel space. So I'm really trying to figure out, if I have a raw set of imagery for a particular location, how can I go about figuring out what area is associated with what type of thing it is? And I'll get more to that in a second. But the goal is to say that, I want to be able to know precisely for an individual address what the square footage of lawn is, what the square footage of trees, and the square footage of pool. And so those are the three main components that make up predominantly the 98% of the outdoor water use for a particular person. So, how much, and that kind of makes sense if you stand back and think about that, people will water their lawns and they'll fill their pools, and depending on where you are regionally, that affects how often you need to do these things. So as you might imagine, in California, you probably have to water your lawn a lot more frequently than you would, someplace that was not in the desert. So, California is interesting because it's kind of a slightly artificial environment. There's a potential for a huge amount of overuse of water because you have people with beautiful landscaping and lush, luxurious tropical type lawns, but it's completely outside of what that climate can support. So really the science behind it is, knowing the square footage of what the current person has in their parcel and understanding how much water is required to keep that particular piece of vegetation alive. So, it's not so much that we want them to stop watering their lawns and make everything die, but we want to be able to give them a scientifically quantifiable amount based on the weather, based on evapotranspiration, which is essentially the amount or the quickness or kind of the time frame in which water will be released into the atmosphere, evaporated, and condensed back down. So there's a very cyclical relationship to that. And as you imagine, that also varies depending on where you are regionally. So, we want to be able to kind of give guidance to people and say, given where you are regionally and given the type of climate that you live in, you really only need to use this amount of water based on the physics to keep your lawn alive or to keep your pool full. And outside of that, you're overusing or you're not efficiently using water. So really that kind of gobbledygook equation up at the top takes into account basically what I said. So the pools, the trees, and the grass, and weighs in the weather and climate and region variability. And so there's also some higher order things that trickle into that too, where if you're on an elevated type of, you have kind of a lot of changes in terrain. So maybe you're on a hilly slope or you're in the mountains or something. Your water runoff if you're irrigating your lawn would be entirely different from somebody who is just, on a flat piece of earth. So that is also a factor that can be put in as kind of a correction. And there's, many other corrections that can be made just depending on the situation and the kind of the geospatial environment that you live in. Does that make sense?
Yep.
Great. So I'm just going to kind of move on for a second, and then we'll get back to water. But really, what is the big question in data science? What are we trying to answer? And kind of in water, I gave you that use case of, where is the water going? How can people be directed to use water better based on physics rather than just conjecture? And to get to that end, it's all about, what can we learn at the pixel level, and how can that be translated to landscaped area, or how, for other types of use cases, how can, a piece of information embedded in a pixel give us an indication of how many cars are in a lot, or how many solar panels exist? There's so many different levels of questions that can be asked, but really it's all about, tailoring the tool set to the imagery type to address that question. And I think the underlying value in all of this is, not just being able to understand the data, but it's all in getting the right type of data and aggregating it and processing it so that you can address the precise question that the business customer really wants answered. And I think this is kind of the departure from more of a traditional researcher or a scientist type position where, often I think the traditional roles of a scientist or a researcher is really in understanding the data, observing whatever the situation is, analyzing the data, and then producing that information, that kind of generalized information to the public, but not really using it to the next level to give some additional piece of insight. So that's the big departure, and that's kind of the underlying goal of data science, and I think also, Omniarth's underlying goal in general is to use physics and imagery in particular to really provide something tangible and meaningful and actionable to someone else. And then kind of at the personal level, I'm really just interested in, I think I'd be kind of happy being locked away sometimes, just playing with all the amazing open source tools that there are. So there's an incredible amount of code that there's a huge user base for right now. And I think, 5-10 years ago, this wasn't necessarily the case, but people are sharing more and more and developing more and more. And so geospatial analytics as a whole has become really dynamic, and it changes, pretty frequently. But because of that, there's just a huge amount of resources available, and that is so much fun to play with. And I'm a little bit of a nerd, so I like sitting in front of my computer and coding and, seeing things happen. And then, but, it's also nice to have the warm fuzzies of, how can you use those cool open source tools to do something with water management, or can you understand the changing dynamics of an estuary? What is the impact of environmental change? And I think all those pieces get pulled into some of the questions that we answer at Omniarth. And really, it's also fun to be super creative. And so I used to work at more of a traditional research lab at the Johns Hopkins Applied Physics Lab. And it was a little less creative. I mean, I think you were more driven by concrete government needs or what you could get funded for a grant. But I think in the context of what we do at Omniarth, it's all about, this dynamic response to a puzzle or a question that a customer might have. So just quickly, a day in the life. I think Chelsea had asked that if I could come up with something to show, like while I was processing, but I haven't really spun up anything this morning. But I just took a quick snapshot of my computer screen, and this is actually a pared down version. So I do a lot of, day to day, do a lot of random coding and what we like to call frankencode. So putting pieces of things together to analyze imagery, and that involves a lot of Python development, I use QGIS. I think you guys might be more familiar with like ARC and things like that. But I get a good visual of the map data, but then it's also just a lot of command line number crunching and then plotting and evaluating things. And the big thing right now is cloud computing, which I'll kind of touch a little bit later, but really, I think in this realm of having so much data and having to ask so many dynamic questions, if we didn't have cloud computing, it would be impossible. And cloud computing, maybe some of you are familiar with. I mean, it's basically having as many virtual machines, computers, that you want and that you pay for. But you have essentially unlimited processing capability, and you have unlimited data storage. And so many people are putting huge amounts of satellite and aerial and database, all sorts of different types of data in the cloud that you can pull at any given time. So, with this, we're at Omniarth trying to architect, the best, most efficient way to utilize all these data sources and pull them in and produce the answers to the customer's puzzles. So that's a lot of my day. Any questions so far?
I think we're good, Shay.
Okay, you can interrupt me at any time. So really, again, it's all about being a pixel master. So what is a pixel master? Obviously a pixel, and maybe not so obviously, but to me it's obvious because I feel like I've been doing this way too long. But a pixel is that fundamental unit of an image, right? And different imagery sources that you may have already talked about have different size pixels. So each pixel can be directly related to a square footage, or it's some type of square area. And so it's all about, within that fundamental unit of a pixel, what piece of information can you get? So in the case of water use, the fundamental question is, how much water should be used to water a lawn and keep a pool? So what do we do to get started with that? And really, you start fundamentally with the imagery. And there are different imagery providers. I just listed a couple that I typically use. We use a lot of Airbus. There's Digital Globe. Nearmap is an aerial provider that has super high resolution data. But all of these products, are provided at different resolutions, which I'll have an example of a little bit later. So each pixel is a slightly different size when projected on the Earth, and you can get different pieces of information. And then once you have the image that you think is pertinent to the question, you need to evaluate that image and understand the data quality. So things like bit depth, so how much information is actually contained within a pixel is critical. And then, how cloudy is the image? Are you going to use 3-band versus 4-band? So, images are typically, when you buy images from a provider, they're in our context, typically multispectral. So red, green, blue are stacked in sandwiches. And then sometimes you can get the 4th band, which is the near infrared. And then there's also the world of hyperspectral, which can have hundreds of layered sandwiches of information. And each one of these layers provides some key to the puzzle. So there's some spectral information that is provided as you add each layer. And the spectral information, it's basically, and again, stop me if you already totally understand this, but the spectral information is really giving you a sense of what can you see at different wavelengths. So it's essentially just more or less putting a filter in front of a camera. So you put a red filter in, you only are going to see things that provide a signature in the red, and then you put a green filter in, the same thing. So as you can imagine, once you start combining, making band ratios and dividing things and subtracting different layers, you can get different signatures of different materials. So that's a big piece of what we do. And then there's other things like pan sharpening, which I have an example of later as well, where that's essentially taking a lower resolution multispectral data set and combining it with a super high resolution single band grayscale image and interpolating between the two, and you can get kind of an in-between somewhere, not quite super high res, but not lower res, so it gives you a more crisp multispectral image. And then the other big thing is doing a lot of radiometric calibration. And so all that fancy work means is that we're taking, for an image, we take electronic counts, or sometimes they're called digital numbers, DNs, and convert that to a physical unit. So, in the actual reality space, what does a digital number relate to relative to, an actual physics-based unit of measurement? And once you get it to that point, then you can do things like relate, how many watts per meter squared do you see in a road versus how much you see on a tree versus how much you see on a solar panel. And all those things can be better understood. And they all are essentially more or less the same throughout the world. So the advantage to converting to this physical unit is that now you can develop a database that can be compared across, throughout the world. You're not just limited to that particular day, that particular time. And then the secret sauce really is all in the algorithm development. And at OmniEarth, we're all about the open source, and that's largely because of our agile work environment. So we're all about kind of producing quick turnaround studies to see if there's actual market value. So really, we're not in the business of spending a huge, exorbitant amount of time and money on developing internal capabilities when it comes to algorithm development. There are already incredibly, amazing scientists that have dedicated their entire lifetimes to do some of this development. So really, it's all about how can we smartly use that, and then we do tweak and add our own tool sets as well. But we're not in the business of reinventing the wheel, and I think that's kind of one of the big advantages of what we're doing. And then really, steps 1 through 5 are just what I deal with day to day. There's a whole other step, 6 through 100 or something of things that happen to actually get this information to the customer. And so I'm not even going to touch on that, but basically this is just a small piece of what the actual customer will see. So one of the big algorithms that I work on, especially in the context of things like our water resource management, is learning from an image. So what kinds of things can you learn? Obviously, when you look at an image, there's a spectral component and then there's a texture component. So, like I said before, you have all these pieces of layered information from the red wavelength, the green wavelength, blue wavelength, near infrared. And they're essentially, you would hope, usually the hope going into it is that once you combine all those pieces of information spectrally, you have kind of a unique data set per type of thing you're interested in. So you want, as a rule, a building will have a unique combination of spectral signatures that are totally different than a tree or totally different than a pool. And so 75% of the time that's true, but occasionally there's some overlap. So you might have like a blue roof or a blue tarp on a roof that looks a lot like a pool. So there's some confusion there. And that's where texture comes in. So the other piece of information you can get out of this two-dimensional spatial space is, can you find edges? Can you find changes in kind of pixel-to-pixel noise level? So essentially texture is just, variable pixel level noise. So like with grass or trees, they're going to have a different texture than a man-made roof. So once we have that information, we can identify or separate things more automatically. And so what we do, in doing that is identify known truth data sources. So to start to actually develop an automated way to process and classify an image, we need to actually go in initially it's called supervised learning. So we go in initially and we say, as a human, I identify that certain pixels are pools, certain pixels are trees, and that's truth. And so it's a small subset of the image that we're, of the types of things that we're interested in. And then the magic comes in training the computer to identify other things that look like the things we know are truth. And this is where the machine learning piece lives. And basically it's all about developing that feature set of saying, typically pools are blue and typically they have this type of texture. That all goes in one class. And then there's a tree, class that they have a specific texture and a specific band ratio. Maybe they have a little bit more near infrared signature than grass. Or maybe there's a slightly different texture, but basically all a machine learning component does is say, you've given me this truth data, and now I'm going to develop correlations between these things. And so that I can feed it thousands of square miles of image and say, go to work and just, you classify it. I told you what truth is. now you understand the correlations and you can do the hard churning. And so that works a lot of the time, and that's also one thing that makes us incredibly efficient and scalable at OmniEarth, where we're not, a lot of other kind of competing companies will do very high precision classification of an image, but it'll be incredibly time consuming because they'll do it by hand. And as you can imagine, that might work really well for a small, like a neighborhood, but once you're doing, you know, the nation or you're doing the world, that's pretty impossible. So it's all about this, you know, how can we teach the computer to know what truth is? And you know, we apply our algorithms, we get a result, and then what? Well, we have to do some type of QA, QC. And that's where the human comes back in and does some spot checking to see, you know, how well the computer performed. And then we also generate this thing called a confusion matrix. And that's basically, it is what it says it is. And it's a table that says, you know, for this one pixel, the human said it was a pool, and the computer said it was a pool. So yay, we performed 100%. But oftentimes, you know, it doesn't work that neatly. So, you know, we might have 50 pool pixels, and the computer said, you know, half of those were actual pool, even though the person said all of them were pool. And then, so we can kind of trace back to see, okay, how did that get confused, and what might we do differently? And then we kind of iterate through some of this stuff. And the last boring piece of text I wanted to show here is, you know, the end goal again is providing the customer with, you know, a high quality, visually pleasing, understandable product. And really, you know, that's all about, you know, making sure that something like a land cover classification looks like what it should be. And this is the tricky part in dealing with some of our customers. You know, it's not all about just the physics behind the imagery analytics. And, you know, if our statistics say that, you know, our computers perform at the 95 percentile of classification, but a customer goes in and sees the result and sees that, you know, a pool was mislabeled as grass or something, that, you know, that's not going to resonate to them. So it's, you know, there's kind of this fine line between, we want to make sure the physics are right, but then we also have to go back through with sanity checks and make sure that we're actually producing what we say we're producing. So this is, so everything that I just described is basically summed up in this picture. And this is land cover machine learning, the results of that. And on the left-hand side is an RGB image. This is Airbus data. So it's 0.5 meter. So each pixel is 0.5 meter by 0.5 meter area. And as you can see, there's like a large community pool, and there's grass, and there's trees. And I kind of, on the right-hand side is the actual machine-produced classification. So I trained it, and I, you know, gave it the truth data, and this is what it generated. And overall, it, you know, sanity-wise, it looks really good. It picked out the pool, it picked out the lawn, it picks out the trees. But you can see it gets a little confused with non-irrigated, which is like, you know, a bare dirt type of surface. It gets that confused with some of the man-made. So kind of typically like the brown roofs, brown shingles, you know, or terracotta, that gets flagged erroneously. So there's a little bit of uncertainty, but overall, I mean, for a machine learning case, it's pretty darn good. But then the question is, I mean, how can we make that better? So to supplement the multispectral data that I talked about, we can add things like LiDAR data. And so I think the world of geospatial analytics is typically very focused on what we call EOIR, so electro-optical infrared, which are the typical RGB type images that you see. But there's this added world of active sensing, which is, you know, actually using lasers or radar to provide additional pieces of information. So, you know, everything I've described up to this point is this passive sensing, where you're just relying on the spectral signatures of the objects that you're looking at to give you an image. And that's largely driven by the sun's interaction with that surface. But in active sensing, you're actually sending out a pulse. So in the case of LiDAR, you're sending out optical laser pulses, and it hits an object and then gets reflected back at you. And that time delay difference translates to an elevation. So now not only do we get kind of a spatial piece, we also get an elevation piece. So we get an altitude difference. And that is really critical for fixing things in that land cover where we misclassified a bare surface with a roof. Now we know that a bare surface is going to be at a totally different elevation than a roof. So we can use things like this to improve the classification, and it gets sandwiched as an additional data source. So the images on the left-hand side, there's this is what we call, it's a digital surface map, a DSM, and so it's hill shaded, so it's kind of, a gray gradient is applied to it to show structure, but that's all basically just LiDAR pulses coming back. So you get that three-dimensional perspective that has that elevation piece. And then the red blobby piece that's kind of next to that on the right-hand side is where I'm actually fusing the LiDAR information on top of the multispectral information.
Shay, we have a question. 1 sec.
Oh, yeah. Sure.
So is this something you would not be able to rectify with NIR data?
Rectify in what sense? What do you mean?
Like man-made from non-irrigated, like
Yeah.
Does it require LiDAR data to rectify these images, or is that something you could do with NIR?
Yeah, that's a great question. And so NIR gets you close, but it's not foolproof. And so, typically we always use the near infrared band to give that information as best as possible. But there are still instances where it just doesn't work. And for whatever reason, there's confusion between the different classification types. Near infrared, you brought up a really good point. Near infrared is an awesome tool to distinguish between vegetation and man-made surfaces. And it also, things like MDBI, which I think you guys are familiar with at this point, it can give you a sense of how healthy vegetation is, and how the vegetation changes over time. But still, these bands, the near infrared, the red, the green, the blue bands, they're all incredibly broad. And by broad, I have a picture later on, but broadband means there's a huge amount of wavelength information condensed into one image. So while you're getting a red image, you're getting a red image over an entire, 100 nanometers or more, something of information. So within that broadband, there's a lot of room for overlap and error. And so, yeah, again, the near infrared gets you most of the way there, but there's still, a lot of confusion between sources. So great question.
About how accurate are we with, if we're just using 4-band imagery on our water use case, how accurate are we? And then how much more accurate do we get when we use LiDAR?
Yeah, so that's also a really good question. So we're still working out some of the details with that, but as a whole, at least for some of our San Francisco area land classifications, we're on average between 85-90% accurate just with 4-band imagery. And that, to give some context, the USGS uses, does an entire nationwide land classification that's machine learning. And their status quo is like 70% accuracy. So, we're up to like 85-90, so a huge jump in accuracy. But then LiDAR, with that additional piece of elevation information, bumps us up to 95 and above. So it makes a big difference if what you're after is really that parcel level information. You want to be able to say, I'm a water district. I want to be able to show my customer that I know where every single tree is on their lot, and I've correctly identified what is a tree and what is grass and what is a building and what is bare soil. I want that accuracy that the LiDAR gives. Otherwise, if you're just interested in kind of, vague, large regional scale information, it's not as critical. So it's, again, kind of all about framing what's significant to the customer. Does that answer your question?
Yeah, totally. We got some more. Keep going.
Great.
Also, how much more expensive is LiDAR?
Oh, great question. So much
more. Great question. It's really expensive. And so, I don't know precisely what we've paid for LiDAR in the past. There are some free sources. So again, USGS has a database of LiDAR data. It's coarse LiDAR data. So the sampling isn't as high resolution as some of the stuff that we purchase. But we're talking on the order of hundreds of thousands of dollars as opposed to imagery, which can be, 10, 20,000, depending on what your, the size. So an order of magnitude. And again, it's like, you want to make sure that if your customer really needs that information, then you need to account for that in your budget, but to buy that data. But if your customer doesn't need that level of information, it's not worth going in the hole over necessarily. So yeah, great question.
Yeah, Maggie, did you have any?
Can you detect where there are trees with grass underneath them, as opposed to where there's dirt?
You guys are killing me. You're asking great questions.
We get this question all the time. It's one of our favorites.
So yes and no. So this particular image that I have on the screen here, this is Geiger LiDAR data. So it's super high resolution LiDAR data. And by high resolution, not only is it sampling at, really close spatial scales, it's also sampling, very frequently. So you're getting like this very high resolution mapping, three-dimensional mapping of what is going on. And with this Geiger mode LiDAR, they claim, the owners claim of this particular LiDAR, that because of the frequency, you can penetrate through the foliage of the canopy and get down to what's underneath the trees. I have not seen that is true yet, but there is possibility. So LiDAR would be the easiest way to understand what's beneath a surface, or if a surface overhangs another surface. In the absence of that, it's incredibly difficult. So, some of the metrics and the rules of thumb that we use with, if we just have four-band imagery are, given the statistics of a particular plot of land, if their entire front yard is beautifully manicured lawn, irrigated grass, then there's going to be a percentage factor that the stuff under the tree is also going to be a manicured lawn. And we can kind of wait for that. Of course, I mean, that could be wrong, right? People mulch around trees, people put flowers around trees, whatever. So there's always error, and I think without the LiDAR or something like stereo, so stereo can also give you kind of an angular perspective of what's underneath things. Without that data source, it's incredibly difficult. So great question.
Yep, we got one more.
Is updated LiDAR information readily available, or do you ever have to wait for collection?
Can you say that again? I missed the last part.
Is updated LiDAR ever readily available, or do we have to collect it or wait for it to be collected?
Oh, yeah. Also, great question. So it's not usually readily available. So typically, like for instance, the free stuff that the USGS has is usually a year or so old, depending on when it was flown. And so, the USGS is kind of in the business of monitoring the nation, geographically. And so they'll do kind of annual revisits of places, but they'll only revisit certain strategic locations. For a lot of the products that we provide at OmniEarth, it's something that we have to task. So we have to say, we have to ask a vendor to go out and collect it over a specific region within a certain time frame. So it requires some planning ahead. It's not just off the shelf, mostly.
Any other
Great
questions?
Any others?
Nope, keep rolling, Shay.
Okay, awesome. You guys are keeping me on my toes. All right, so this is just another example of some of the stuff that I've looked at and developed algorithms for. And so this is kind of more of a car counting feature extraction algorithm. So like I mentioned before, the spectral information gives you certain pieces of information, but then also the texture and kind of the geometric pieces of information at a spatial level can give you additional pieces of information. So this wasn't a completely successful algorithm, but you can kind of see that the algorithm outlined where cars should be in a particular lot. It found edges of buildings. It gets kind of confused around shadows. But again, another analytics piece that is useful, not necessarily just as itself, but once you start asking the questions, how many people are visiting my shopping mall in December? How many people are coming in to buy stuff? You can do things like count cars to see, for any given day of the week, for any given month or season, how many people are visiting a location. And then kind of the trickle down effect is, given that piece of information, what does that say about the state of the economy? Like, are people more likely to go to the store and buy stuff? Or, so there's a lots of kind of higher level questions that can be asked once the lower level analytics are addressed. But often bad things happen when I develop algorithms. And so this is one thing that we've started tweeting about called the Gallery of Dreams at OmniEarth. And they're algorithms that have gone awry and have somewhat created art. And this kind of is fun for me because it helps with my art background. I have a nice little outlet and a break from the physics, but some of the products of this, the garbage, creates really interesting art pieces. And so I think I can describe a little bit about the algorithms here. These are all kind of an attempt to extract texture and buildings. The one image on the left-hand side, actually, it looks something like, a southwestern sunset or a mountain, but really all those little tiny pinpricks dots are parcels and buildings, and I was trying to actually extract footprints of buildings in San Francisco. And then if you kind of go down, the middle piece where it looks like blobby circles and asteroids or comets going through the screen, that again was trying to develop correlations between different spatial scales of things. So trying to identify things with like textures. And this was all around a stadium in Berkeley. And it was not a successful algorithm, but it made an interesting picture. And then the last one on the right-hand side was again trying to extract specific buildings. So there's a lot of interest around automating building footprint extraction. And if you have something like LiDAR, it's pretty straightforward because you have that elevation, you can identify that pretty quickly. But in the absence of that, how can we automate pulling out buildings or pulling out specific features? And you can kind of see there's a road with a cul-de-sac running through it, and it gets some edges, but it doesn't get all the edges. And so this is definitely a complicated problem, and a variety of different companies are working on this. The general consensus is that you kind of have to do a lot of it by hand, which is really unfortunate. But one day we'll have it figured out, I'm sure. So.
Shay, some of your Gallery of Dreams is actually on our course website.
Oh, awesome! Yay! Well, I think
yeah, that's what the headers. A lot of them are Shay's LiDAR and Shay's land classifications. But she actually does have a very cool Twitter feed that puts all of these things out there, and it's pretty great.
It's fun because I would say 75% of my job results in like things that don't work. And I got really frustrated initially, like I have nothing to show for what I don't produce. And so now I think showing some of the iterations of things and showing that they're interesting in itself has been a little bit validating, so it's useful. I just wanted to talk a little bit about some other aspects that we can use imagery for. So like change detection, I don't know how familiar you are all with that, but it's pretty straightforward in concept. It's really taking different timestamps of images and understanding what's going on, what's being built, what infrastructure is changing. And this is actually interesting image set in that it takes 4 different imagers. So a digital globe imager, Skybox, and the Thea Earthcast image for various different times and looks at a change and a buildup in a refugee camp in Jordan. And so if you kind of walk through the timestamps in 2013, it looks like the infrastructure is getting built and there's actually a lot of bright stuff, so it's a lot highly populated. And then it kind of decreases in population and becomes much dimmer in 2014 and 2015. And then if you kind of jump down to the lower level and the Thea imagery, there's slightly different timestamps, but you can again see this time transition of the buildup of things or the influx in this case of refugees. And often, when we're trying to tackle certain questions, there's a time piece to it, right? There's every question has a time relevance associated with it. And this is one of the areas that OmniEarth is going to be more competitive than other companies eventually, because we will have imagery every day, everywhere. So a huge amount of data, but very timely data. And right now, kind of the state of the state is to, you're subject to whatever data has been collected at whatever random time, unless you happen to be able to cue a satellite or be able to give a satellite a command to look at something. So you have to interpolate a lot in between the times of things. So you don't necessarily get a full picture, but there's a huge amount of information that can be done looking at the times, the rate of change of something. And then this was just an example, there's a seasonality to that change. So, in the case of agriculture, as you imagine, there's different crops will, be harvested at different times, and different things have different growing seasons. And, I think on the OmniEarth side, we're really interested in, at an agricultural perspective, can we identify how much water would be used by a specific type of crop? And for their duration of crop cycle, what does that profile of water use look like? So having a seasonality of the change in vegetation using band ratios like NDVI or EVI or various other band combinations, you can start to understand that rate of change. And so again, it's this dynamic, evolving perspective. And I think oftentimes the geospatial analytics are just forced to be very stagnant because of the limitation of available data. And so I'm going to quickly go through this, but some of the challenges, I think I've touched on a lot of them, but again, having the right scale or the right resolution of the image to address the question that you're interested in is a big challenge. And then, of course, the color, what kind of bands, what spectral information do you want to pull out? Can you calibrate the data? That's been a pretty critical one for OmniEarth. Can you combine the right type of information? So, often there's a huge amount of information out there. What are the pieces that you need? And that's also part of that secret sauce of being a data scientist, is identifying what the pieces are. And then what kind of corrections need to be made to the imagery, for instance. You have to correct for atmosphere, like dust, haze, scattering, clouds. And then do you have the right time signature to address the problem that you need answered? So on the scale side, some of you might have already seen this type of image, but basically, you have a high resolution image that you can easily see the City of Boulder water treatment plant. As you zoom out, you get bigger perspective, you get an agricultural landscape, you get kind of the surrounding urban areas. You keep zooming out, now we're at a Landsat image. You can see that, Boulder's one tiny little pocket in a larger, on the edge of the mountain range there, and you get a larger geospatial context. And then we move to MODIS data, which is 1 kilometer now. So Landsat was 30-meter pixel sizes. MODIS is 1 kilometer. So now you're resolving things at kind of the state level. And then GOES, which is couples of kilometers. So, GOES imagery gives you now a sense of on the Earth as a whole from geospatial orbit, the highest possible orbit that you can be in for a satellite. What is kind of the overarching weather or the dynamics of the actual atmosphere of the Earth? So, again, it's all about picking that right scale of information, coupling that with the other pieces of the question that you need. And then for the color, some of you are probably aware of this as well, but there's spectral information like we've talked about, and different bands of an image provide different pieces of information. And so this is kind of a little cheat sheet. Most of the stuff that we do in geospatial analytics today kind of sits in this visible wavelength range, and then you'll get often near infrared band, but there's a huge amount of information beyond that. And from my astronomy background, this is a tenth of the amount of information that's available. So the spectrum keeps on going, way out to larger and larger wavelengths. So again, you can get additional pieces of information, but this is a little bit of a cheat sheet in terms of the types of band combinations you would want for different things. So, for instance, oil and gas, you might be looking specifically at shortwave infrared bands, which are further out on that solar radiation tail. And then, soil and vegetation are kind of mid, visible wavelengths, land classification, visible wavelengths. But there's just a variety of different applications. And so this is kind of the Landsat bands overlaid in blocks of colors here on top of the atmospheric transmission spectra. So the other thing to think about when you're selecting the data types is, can you get the piece of information you want from the sensor, whether it's satellite or aerial or whatever you're using. Atmospheric transmission, we also call them windows. So, everywhere you see that dark gray, that means you can look through the atmosphere. So, in the case of Landsat, I'm never going to be able to look through the atmosphere at 1900 nanometers. It's completely opaque or black to me. I can't see anything. But if I look at the visible wavelength range between 400 and 900 nanometers, there's a lot of pieces of information I can get of those different numbered bands. And kind of the cheat sheet scale on the bottom, the different bands give you pieces of information about aerosols or vegetation or other things. So that's kind of spectral physics in a nutshell. But the idea is not only, as a data scientist or a scientist in general, you use the imagery, you have to figure out where, what pieces of the imagery, that you can actually utilize for your problem, and then, what is actually available for you to use. And then, again, the spectral information is incredibly valuable because different things have different spectra. So if you look at the kind of the reflectance at the bottom, the big thing I want you to take away is that, corn, tulip, poplar, and soybean are all vegetable, vegetation, but they have different spectral signatures. So depending on when you look at them, like if you look at them strictly in the visible, which is on kind of the far left there, they're a little hard to distinguish, especially this tulip, poplar, and the corn. But as you kind of move out in the near infrared and the shortwave infrared, there's a lot more separation. So you can start seeing differences between vegetation types. But this, carries over to not just vegetation, but lots of other objects in your scene. And, again, just a little snapshot of vegetation. Plants are really good at, emitting infrared vegetation, infrared signature. So, they're going to absorb almost all the red, green, and blue, but, we see them really well in the infrared because, they're converting all of that red, green, blue visible wavelength into infrared as they're exhaling or breathing out their signatures. So, that's the piece that we see. And I think the background layer is just some hyperspectral band ratios. So, again, all in this combination of bands and what you select in terms of, the types of information you want. There's potentially a not infinite amount of information there, but a huge amount of information that you can tap into. And I think I have a last couple little pictures here. So this is, here we can kind of see the Zambezi River Delta. We see sediment churning up in the open water. We can differentiate various things going on in the scene. We see the vegetation. We probably see kind of a more bare or mountainous region. And, we can look at these things in different wavelength bands to really identify the dynamics of the situation, but then also, precisely what's in the scene. And then from an agricultural perspective, this is just a snapshot of different fields. So within each one of these fields, potentially are different crops. And so this is where having the spectral piece combined with the time piece of multiple images over time, over a growing season, can you start understanding the dynamics of how the scene is changing and what kind of crops are being used. And then on the correction side of things like scattering. So here we have sun glint off of the surface of the water. So that can be very detrimental in terms of trying to understand signatures of things. And it's something, unfortunately, you have to deal with in the visible wavelength. But, so choosing imagery at a specific time of day is critical. Pen sharpening is also a piece that we have to deal with. And that's, I mentioned to you earlier about, essentially the basis of pen sharpening is you take a lower resolution multispectral image, you fuse it with a high resolution grayscale image, and you get a combination of the two that can provide some more information. And it's much cheaper that way. So you're taking high resolution data at one wavelength and you're combining that to multiple wavelengths. And then, the atmospheric correction, clouds, snow, haze, fog, it can all be confused with each other. And so these things have different spectral signatures, they have different time scales. So, snow might subsist longer or remain longer, persist on mountaintops than clouds, obviously. And then, fog and stuff can move around. But all these things prevent challenges to the scene dynamics. And I think I touched on this a little bit before, but how does OmniEarth compete in this whole realm of satellite imagery and aerial imagery processing and data science? But really, it's all in this agile development of getting accurate, physically verifiable ideas out quickly to the customer to see, is this of interest? Is this what you want to see? We're not in the business of dwelling on the minute details of the research necessarily. If we have a customer that's really interested in a problem that we kind of architect and are willing to pay for that or invest in that, then we can jump down all those rabbit holes. But really, it's all in this quick turnaround. What can we do in a week or a day or something like that? And then a couple of other places where we compete is in this use of mixed data sources. So as you can imagine, using all these different types of data requires a huge tool set, and a lot of people don't necessarily know how to use all of them. So we pride ourselves in finding people in the OmniEarth family that can do that. So we have people that know how to analyze LiDAR data and synthetic aperture radar data and multispectral data. And so it's bringing all those pieces together to make this comprehensive solution to a problem. And because of that, we're also very data agnostic. So we're not subscribed to one particular data type. We don't care what the data is, just whatever works to solve the problem that we're interested in. And then we all go open source, right? So I mentioned, we don't have the time and the manpower necessarily to develop these incredible algorithms that people have spent lifetimes doing. So we try to use what has been published and what is available and modify as needed. And then, kind of running this line between always basically constructing the car while we're driving it. So, we're doing R&D while we're producing products, and, the products that we produce are also back, informing what R&D should go into it. So it's this cyclical, crazy roller coaster ride, but I think it's proven to so far be pretty good. And then kind of the other piece that we didn't touch as much on, but I had mentioned that, really we couldn't do any of this without cloud computing. Like, again, 5-10 years ago, none of this data was available, and it was really expensive. Imagery was much more expensive. All this open source stuff was not just around. So there's so much data, but then, one laptop is not going to be able to process all of this. So by working in the cloud with Amazon Web Services, or, there's other options that way, we can essentially have a huge server farm, but not have to do any of the maintenance. And we can host all these different data sets and pull from different things without the cumbersome, need to own any of it, really. And yeah, so I think that kind of sums up the technologies or improvements that really drive where we are today. So I think that's all I had right now. How about some questions? Do you guys have any more questions?
What do we got, Emily?
You talked that you use QGIS. Have you had any shortfalls in using an open source format?
Oh, so many shortfalls. Yeah, I mean, I think, again, we kind of go cheap and free. I mean, we're not opposed to buying stuff if we need to. And I think QGIS gets us usually 95% of the way there. But there is a lot of question in general with going open source, right? Because you're relying on the goodness of somebody to maintain it or update it. And so there's pitfalls with that. They could stop supporting it, or they could, there could be a bug introduced that nobody can fix, or, but I think as a whole for QGIS, it has been, I mean, I haven't really used ARC, so I can't fairly compare it, but for all my needs, I think it has served really well. Great question.
We've read a lot about the Planet Labs and those satellites. Do you foresee using kind of data that's updated that constantly in what you do?
Oh, yeah, absolutely. I mean, and on Labs in particular, we've looked at some of their data. They have had a lot of issues with their imagers. So I think they're always in this oscillating, trying to fix the imagers and have, high quality data products. So we haven't used some of their data quite as much as we'd like, but yeah, I mean, once we have, for OmniEarth, and I don't know how much, if Lars had mentioned this or Chelsea or whatever, but we're going to be launching this constellation of satellites that will provide data everywhere, every day. So that's the tagline. And so we'll be getting terabytes of data daily at the exact same location every day. So, potentially, just a huge amount, fire hose of data. And all of that has to live in the cloud. So again, we wouldn't have been able to do any of this without this cloud infrastructure of being able to have as many servers and databases as infinitely we need. So yeah, and it's a little scary and daunting, and a lot of the analytics that we're building now is going to support that frequency of data eventually. So everything that we're doing is a foundation leading towards pulling in this high frequency data.
Yeah, and I would add to that too. We're going to be collecting our own data, but we've taken a little bit of a different approach to the data, the satellite world, I think. And we'll talk a little bit more about that either today or tomorrow, because we looked at Planet Labs and we had readings about all these different sat companies. And Shay mentioned the idea of being data agnostic. And so even once we have our own satellites, that will remain true. So if Planet Labs fixes their imagers and we think their data is good enough, because right now we don't really think their imagery is that great or consistently good, we will use whatever is out there. And, we buy imagery from a host of different providers. We use a lot of open source imagery. So we will not, I would say we won't necessarily say, oh, we're never going to wed ourselves to one data source or one tool set, because we think that that's kind of the way of the past, and the way of the future is to be able to kind of use everything that's available to you to derive better insight. So we would probably, we'll use our own data for sure. But
are you able to look at it before you buy? Can you go through and whether or not you want to use it?
Yeah, you do. So like what you guys saw yesterday with Landsat, a lot of companies like DG, Airbus, they have like a store, and you go on and you look at all the different images and you decide if it's what you want. If it's a really big package, though, right, Shay? I mean, you're not going to look at, if we're buying the whole state of California, you're not going to look through every tile. But
Right. But and I think sometimes, we've been, especially with aerial vendors, so people that are just slapping imagers on airplanes. They'll give you a sample region, so maybe a couple miles or something to evaluate, and we see a lot of differences in the quality of the imagery, and so I think when you get onto some of the, like, you're going to buy imagery from a big provider like DG or Airbus or something, I think you kind of know what to expect, and you can look at those thumbnails, snapshots. Oh yeah, that day looks good. I'm happy with that. I know how to work with it. But with some of the aerial providers, we actually need more than that visual confirmation. We need the actual data sample. Like, give me the pixels so I can make sure that I know what it is. And so we do that as well. And I think we're building some relationships to be able to do that pretty efficiently.
Maggie, go ahead.
I think you kind of started to answer this question, but is there like a learning curve of getting familiar with different data that you use, and can you write an algorithm for one set and apply it to another set?
Yeah, there's so many learning curves. And I think, so personally, coming from astronomy, it was, I did a lot of this already for different types of data. So I never really looked at the Earth. I was always looking at other things. So I was looking at gas giant planets and stars and pulsating variable stars and galaxies. But the basic understanding of how to process an image is straightforward. I think the novelty and the learning curve has come with, for me, at least at a personal level, is understanding all the geospatial tools and how, what the language is and what to expect. I think the physics, fortunately, is always the same. And I think that's the beauty of what we do, is that, we don't necessarily need to know every geospatial thing in the world, but we know the physics, and that's really helpful. I think on a product side of things, the difficulty is in dealing with some of the different imagery sets. There's always a learning curve when you introduce a new type of imagery. So things like DG and Airbus are very understandable. Like, they've been around, they give you all the information about calibrating, and you have all the details. But some of the newer imagery providers don't provide you with that information. And and when you develop your algorithms to do some of the machine learning or various things, it's kind of you just have to try a bunch of stuff to see what works best for that imagery type. There's learning curves all over the place. That, coupled with the fact that, at least when I started, I was not a machine learning person at all. I didn't know really how to do it. So there's a huge piece of learning, what are the best classifiers to use? What is the best algorithm? I mean, it's always this constant scramble of trying to figure out what the best thing or the most appropriate thing is. So, my entire life can be described by a learning curve, I think.
Any other questions? No? Bill.
Shay, this is Bill Hegman. Shay, I have a question. Maybe you can give us some insight. I'm just trying to get some context here. When we looked at the data set for Folsom, California, so we have a sense for what that looked like in the area and so on. So we played with that. Can you give us a sense? I mean, that was maybe was that an example data set that you
Yeah, so we were on the demo system, Shay, using the test stuff from Folsom, which I think is half meter.
Okay. Can you give us a sense of what kind of time are we looking at to say, develop those learning algorithms and to get things really working on the end of what you do? Is this months or is it weeks? And then also about the scalability of it. Does it get better as you learn and then go on to another area?
Yeah, that's a really good question. I think 6 months ago, it was on the scale of months, and that was largely because we didn't really know the tools that we needed, and we were still trying to identify everything. Now, for something like Folsom, for that demo region, from raw image to land classification, that was a couple hours, and then we kind of have a couple handoffs where we'll have a different teammate actually run the water budgets, and a different teammate will upload it into the platform so that you actually have that nice visual. So maybe a day or two. So a huge difference from initially, months to a day or two. And I think that has pretty much been consistent. So a lot of it, I mean, as long as we stay with known imagery sources and we don't have to figure out new data sources. At this point, we have, 5 or 6 different sources of data that we typically get, and that we know how to tailor our algorithms to. So it has become so much faster, and potentially, my goal is to remove myself from the equation as much as possible when it comes to land cover, and just have it all automated in the cloud. So, in principle, we would have an OmniEarth image come down from a satellite. It would go to a virtual server. All of the code would be there. It would be, the land cover classification would be applied, because we would have a library of truth data that somebody already painstakingly put together. So it would be kind of an automated thing. And so we would go from months to hours to, in a year from now, hopefully seconds or less. So, definitely. I mean, the whole archetype of what we're doing is all about scalability and how can we do it faster and essentially write ourselves out of the equation, more or less.
Awesome. Well, I don't know if we have any other questions, Shay. I know we kept you longer than we should have, but this was great. Thank you so much for calling in. I appreciate it.
You're welcome. You guys were a great audience. Thanks for your awesome questions.
Absolutely. All right, we'll talk to you later, Shay. Thank you.
Okay, thank you. Take care.
Okay, that was excellent. Good questions, guys. Leave meeting. Cool. Very cool. What'd y'all think?
I was wondering if people were confused about. I think most picked up most things, but there was something she mentioned about the spectral resolution.
Mm.